So now what we want to do is create the footprint for this part. In the PCB, we have the schematic side and the PCB side. So in the schematic, we have all these symbols that we will show, that we'll use to show all our wiring diagrams in our connectivity. But on the PCB, we need an actual footprint with pads that our ICs can actually connect to. So for this one, if we go back to DigiKey, the NE555, you can see that this is some IC. We'll check out the package down below. This is an 8 SOIC, so this is a very standard PCB component package. And if we click on the datasheet again, at the top of the datasheet, we should see all the different packages that are offered. So, where are you? Sorry, that's not at the top, it's at the bottom. So at the bottom, we can see the package outline dimensions. We have a SOIC 8, and let's just double check that DigiKey had the same one. Yeah, that's right, 8SO. And from here, we can see all the physical dimensions of that IC. And we can use these along with Altium to create a really nice pad layout. So if we keep this in mind, we go back to Altium. We're in the schematic library tab. So we're going to go back to the projects tab, right click on the project, and add new to project. Now we're going to create all the footprints, call it the PCB library. So this new tab will show up here called PCB library. If we go back to projects, we can see that within our 555 project, there's a libraries folder, there's a PCB libraries folder for the footprints, and there's a schematic libraries folder for our schematic library. Since we created this new PCB library document, our project has changed, so let's save it again. And we'll add the PCB library file to our project. So let's call it footprints. Save. Cool. Let's go back to PCB library. And what we can do here, there's a really nice tool from Altium called the IPC compliant Footprint Wizard. IPC is basically standard for footprints across the world so that we can create nice pads like this that are standard, so that manufacturers can create parts that fit in everyone's PCB properly. So Altium has a really nice selection here of all these different types of footprints you can make. They show a nice little graphic of different parts. So the one we're looking for is a SOIC. It's a small outline integrated package or integrated circuit. You can click on it. This kind of looks like what we saw in DigiKey here. This guy. Cool, so let's hit next. And we're given the option here to specify the exact physical dimensions of our integrated circuit. And luckily we know those from the datasheet. Usually the section is always at the bottom. So let's see, what does Altium want? They want the width range, so that's H. So that's the total width of your IC. And there's always a minimum and a maximum, mostly because when you create parts in the factory, not every part will be exactly the same. You'll have a little bit of tolerance on the dimensions. So just to be safe, Altium and most EDA softwares will include a min and a max so that you have a little bit of tolerance on your pad size. So the minimum, and you can see inside here in the datasheet, we always also see the min and the max. So the minimum total width, that's E, is 5.90. All dimensions in millimeters, by the way. 5.90 millimeters, and the max is 6.10. So 5.90 mm, 0.10 mm. Yeah. Maximum height, A. That's the total height. So that's maximum height is A here. A, note there's no min for A. We just want to know the total maximum height. 1.75 millimeters. And this will slightly change our footprint as we keep adding components here. The body width range is E, so just the body without the leads. So in the IC, the actual plastic part is called the body, and that holds all of the microelectronics inside. And these conductors here are all called leads, and they'll connect to your footprint pads. So you're looking for the body width range. That's E1 in this case. Min is 3.85, max is 3.95. 3.95, and then you can see that our footprint changed a lot here. So we have to have a really skinny body. Body length range is D, how long our thing is, our IC is. Minimum is, let's see what the minimum is. So that in this case D here, 4.85 to 4.95. How many pins do we have? Well, we know it's a SOIC 8. 1, 2, 3, 4, 5, 6, 7, 8 pins. So 8 here. And the lead width range, so that's basically how wide our leads are. Let's see, it's B. And in this case, it's this lowercase b here. So it's 0.3 to 0.5. It's pretty close to what the default is already. We'll change just a little bit here. Not even noticeable. Lead length range, L. So that's just the length of the lead that's touching the PCB. See that right here, this L here. 0.62 to 0.82. Oh, that's a meter. 0.82. Cool. And the pitch, which is the distance between the pads, are standard for SOIC, so they'll be 1.27 mm. Let's just double check in DigiKey. Sorry, in our datasheet E here, 1.27 typically. Okay, so this is what our footprint is going to look like. You can see that there's a body here. This pink kind of hatched shape is where the physical body of the chip will be. And these red pads are going to be exposed metal on our PCB that the leads will touch and that the leads will touch and be conductive with. You can notice this little dot here. This yellow, all the lines in yellow indicate parts on the top overlay of the PCB. It's sometimes called the silkscreen. This layer is just to show reference designators like, oh, this is R56 or U13, and also any useful information you want to put, maybe your company's name or your name, or any notes or helpful guidelines you need to operate the PCB. This little dot will also show you pin 1 of the IC. So on your footprint, we're going to have to figure out which pin is connected to which pin in our schematic, right? Remember, we had our component here with 8 different pins that all have different functions. So it's pretty standard usually to start in the top left with pin 1, and you'll see whichever one's pin 1 with this little yellow dot. And you would go down counterclockwise. So 1, 2, 3, 4, 5, 6, 7, 8 would be the ordering. If we hit this 3D button, we can see what the chip would actually look like in 3D on the pad. And if you hold Shift and use your right mouse button, you can drag the component in orbit around it. Note that this is just kind of a box, right? If we want to see a nice 3D model of the integrated circuit, we can click this Generate Step Model preview in the bottom left. And there we go, there's a nice SOIC. So at any time we want, we can go back to 2D, make sure we see it, looks good. And in the 3D, we can see what it actually looks like. This will be really nice when we generate a 3D model of our PCB. Let's go next. A thermal pad is just an exposed copper opening right underneath the body. It's not going to be connected to any pins, it would be right here, but it's really useful for thermal relief in case your integrated circuit gets really hot during operation. And you have to check in your datasheet if your integrated circuit has exposed copper on the bottom of the plastic as well to connect to the PCB. In our case, it doesn't because our chip is mostly signal related, doesn't get really hot, so we should be okay. These are min and max values. We'll leave them as standard. These are standard as well. Intolerances, we can just use the calculated ones from Altium. Again, keep default. And here, if we're not happy with the generated dimensions from Altium, we can manually change them. But especially for standard parts like SOICs and QFPs and QFNs, usually do pretty well. So you can just check here X. So Altium wants to make the actual pad width so at the pad width is this one, 0.6 millimeters. So if we go back into here, to our data sheet, Diodes Incorporated recommends the pad to be 0.6 millimeters in width, which is exactly what we have. Great. And Altium says the length should be for Y 1.45. 1.55, we'll probably get away with 1.45, should be okay. C2 is 1.27 standard, and the total length 5.45 from C here to here should be good. Here you can choose the pad shape, rectangular, rounded. It doesn't really make a difference. You can pick whatever looks nicer for you. People do like to justify things in any way they can, so they'd say that a rounder pad will have less stress concentrations because there are no sharp edges, and you'll get a nicer solder joint. So I usually just stick with rounded, but it really doesn't make a difference, whatever you prefer. Next, silkscreen is that yellow layer we talked about before. And it basically will just show a nice little outline for our chip, and also where the first pin is. Also, this big yellow one is the same function as the small yellow one. It's just that when you place the component physically on here, you won't be able to see this big one anymore, so this yellow one is right outside. You can also notice a little green bounding box here. That's another mechanical layer that basically bounds the total volume, or the total area taken up by our IC. Next, courtyard information. That's the screen bounding box. We can leave it just like this. Should be okay. Suggested values. And here's where you can specify where you want to save it. So we want to save it into our current created PCB library file footprints, and we want to produce this 3D model so it looks nice. Next, we're done, finish. Awesome, so we have a really good footprint right now for our part. You can see it here. And let's just rename it instead of this really gross name. It's kind of difficult to tell. Sorry, it's edit here. Let's just call it SOIC 8. Okay. So to pan around, you can use the right click, and to zoom in and out, I think it's Control mouse wheel, but I changed mine to just mouse wheel as zoom in, zoom out, as I think that's more comfortable for me. If you want to change that, you can go to these settings here. It'll be in system, mouse wheel configuration, and you can set whatever you want. So for me, my main zoom is right on the wheel with no control or shift. Great. So we're almost done for this part of the video, of the tutorial. You can save this. On your keyboard, if you hit the number 3, you'll switch to the 3D view. If you hit number 2, back to 2D. So 3, 2, 3, 2. And in 3, again, if you want to orbit around, you hold shift. You get this nice kind of sphere. And you can use your right mouse button and drag to orbit around your part. You can see it's some nice pads, a nice silk screen, and the 3D model of the SOIC 8 looks really nice. If I want to reset my view, I can hit the number 0. I can go back to here, hit the number 9, I'll rotate 90 degrees, back to 0, back to 9, back to 0. If I hit V like Veronica, and then the letter B, you notice that each one of these has a little underline. If you hit whatever letter is underlined, you will activate that command. So flip board, if I hit B, I'll flip whatever is in this 3D view. So if I hit V, B again, B like banana, I can keep flipping. All right, that's it. So we've created a schematic part, and we've also created a footprint for that part. So if you want to relate them together, right now our schematic part has no knowledge of the footprint. We can hit this, make sure we're in the schematic library, hit this add footprint button. And we can just browse. And in our footprints library created, we have this SOIC 8, which is perfect. Okay. And now our 555 timer IC is linked to the footprint that I created for it. So we're completely finished making this part. The next video, we'll go through making the resistors and capacitors, and also the LED that we need to finish our timing circuit. Thanks, guys.